Okay guys, so this is part 2 of the lesson on the derivative of parametrics. We went through part A and now we're going to go into part B. In part A, we established that dy dx was the derivative of the y component divided by the derivative of the x component, or dy dt over dx dt, or y prime over x prime, and we came up with 3t squared minus 3 over 2t. Part B asks for the points on C where the curve, where the tangent line is vertical and where the tangent line is horizontal. Okay, if we refer to what the curve looks like again, and now I'm realizing that my picture is a little crooked, but I can see horizontal tangent lines and I can see a vertical tangent line. I see one I see one vertical and 2 horizontal tangents. Look for them, label them, pause the video, come back to me. Okay, so I see my 2 horizontal tangent lines and my 1 vertical tangent line. Okay, we might be able to figure out where these are without much calculus just by looking at that graph, but we need to be able to do it with calculus, okay? So I want you to think about how I'm going to find a vertical tangent line and how I'm going to find a horizontal tangent line and what each of those things mean. Pause it, come back to me. When do horizontal tangents occur? Well, horizontal tangents will occur when dy dx is 0, and dy dx will be 0 when the numerator of that fraction is 0, so when dy dt is 0. dy dt is 3t squared minus 3, so we need to set that equal to 0. If I do a little factoring and solving, I will get 3 times the quantity t squared minus 1 equal to 0, and that's equal to 0 at t equals plus or minus 1. Now notice that I didn't ask you when the points on the tangent line is horizontal. I asked you where are the points on where the tangent line is horizontal. So we need to figure out what the xy coordinates are. So go ahead and plug those t values into your x equation and your y equation, your x component and your y component, and you'll get the coordinates of those points where that tangent line is horizontal. Okay, so plugging in t equals 1 to both the x component and the y component, I get the point 1, negative 2, and at t equals negative 1, I get the point 1, 2. Okay. Alrighty. Moving on to vertical tangents. Vertical tangents are going to be where the derivative is undefined. And dy dx will be undefined when the denominator of that fraction is 0 or dx dt is 0. Okay, that means I need dx dt or 2t to equal 0. And that's happening when t equals 0. Now again, you weren't asked to find the time when the tangent is vertical. You're asked to find the point where the tangent is vertical. So you need to plug that t value into both the x component and the y component. Okay, so at t equals 0, x is 0 squared, which is 0, and y is 0 cubed minus 3 times 0, which is also 0, which means I have the point 0, 0. Okay, so we have horizontal tangents at the point 1, negative 2. And 1, 2, which I see, if I go back to the picture, I see that I have 1, negative 2. I'm sorry, that's 1, 2. 1, 2, and 1, negative 2. And then my my vertical tangent at the point 0, 0. So the points that I'm getting make sense. All right, let's move on to part C. Part C asks me where the curve is concave up and where it is concave down. Okay, and concavity always requires me to use information from the second derivative. So I'm going to need to find the second derivative. And in the first video, we established that we find the second derivative by taking the derivative of the first derivative and dividing by dx dt. Okay, so the derivative of the first derivative divided by dx dt. Now the first derivative looked like this. As a general hint, when you're taking the derivative of the first derivative, look at the first derivative and see if you could simplify it in any way. There's nothing in common, numerator and denominator. I could break it into 2 terms, but it's just as quick for me to quotient rule this. But if I can avoid quotient rule, you'll want to avoid quotient rule, okay? So when I go to take the derivative of the first derivative, I'm going to use quotient rule. So I'll have that the second derivative will be bottom derivative top minus top derivative bottom over bottom squared. So go ahead, pause the video, come back to me. Okay, so here we have the derivative of the first derivative. Okay, bottom 2t times the derivative of the top, the derivative of 3t squared minus 3 is 6t, minus the top times the derivative of the bottom, the derivative of 2t is 2, over the bottom squared. Okay, and now I have to divide this by dx dt, and dx dt is my 2t. Okay, so I'm going to take this entire thing and divide it by 2t. And let me put that nicely for you. Okay, so I divided the entire quantity by 2t, which was my dx dt, and what I can do is just simplify this a little bit. Okay, so simplify, pause, come back. I simplified the numerator to be a 12t squared minus, I distributed that 2, I had a 6t squared plus 6, and the 2t squared divided by 2t I made into a divide by 2t cubed. And simplify that even further, and we get 6t squared plus 6 over 2t quantity cubed. Now, if you remember, when we're looking for concavity, or changes in concavity, I want either the second derivative to be 0 or to not exist. Okay, so first of all, ask yourself, where is the second derivative 0? Pause and come back to me. Okay, okay, and this is going to equal 0 when the numerator is equal to 0, and if you look at that numerator, it's it can't be 0. Okay, so if the second derivative can't be 0, we also need to consider where the second derivative doesn't exist. Okay, so the second derivative will not exist at t equals 0. Okay, if we do a quick sign chart to determine the concavity where we're concave up and concave down, you can make yourself a little sign chart for the value of the second derivative, if it's positive or negative, to the left of 0 and to the right of 0. Okay, so the second derivative is positive when t is greater than 0. It's negative when t is less than 0, meaning that the curve will be concave up when time is greater than 0 and concave down when time is less than 0. Okay, and we just need to give this information in a good way, so let's label that. Okay, so we're concave up when t is greater than 0 and concave down when t is less than 0. Okay, so that is it for the derivatives of parametrics. It was one problem, but 3 good examples of what we can do when we're taking a first derivative or a second derivative. We can find equations of tangent lines. We can find where tangent lines are vertical, where tangent lines are horizontal. We can take a second derivative and find the concavity of a graph. We could see where the graph is concave up or concave down. And this is pretty summative of what we're going to be asked to do with our derivatives, both in a college level Calc 2 course and in terms of the textbook style parametric equation problems on the AP exam. I am going to throw in arc length in this lesson, although I don't know that we'll get to it in class tomorrow. Arc lengths of parametric, it's just a formula very similar to our arc length formula for rectangular equations. But because I don't have a single function that I can take a derivative of, I take the derivative of the x component and square it, take the derivative of the y component and square it, add them, throw them underneath the square root, and integrate it on the interval. Okay, so for example 13, okay, if I want the derivative of the x component, the derivative of the x component would be the derivative cosine is negative sine of t. The derivative of the y component, the derivative of sine is cosine of t. Okay, so I would take the derivative of the x component and square it, add on the derivative of the y component and square it, throw that underneath the square root, and integrate it. Now my integral, now I got t's inside my integral, which means I need a dt at the end. And because everything is in terms of t here, I need to have t values for my bounds. Okay, so I would go ahead and do this. Now, this is the arc length of the unit circle, so I'm going to ask you to go ahead and integrate this one by hand. It requires your knowledge of the trig identities, or your main trig identity, but I will tell you that just like the arc length of rectangular curves, the arc length for parametric curves, 99% of the ones that you come up with, or maybe even more than that, will not be integrable by hand. Okay, so you'd have to have a calculator to integrate it. But this one, you guys can go ahead and integrate this by hand, and I will do it for you after you pause the video and come back to me. Okay, so the integral that I had was the integral from 0 to 2 pi of the square root of dx dt quantity squared plus dy dt quantity squared dt. If I simplify this a little bit, I get the integral from 0 to 2 pi of the square root of cosine squared plus sine squared dt. Now I said that you guys needed to use a trig identity, and hopefully you recognize that cosine squared plus sine squared is equal to 1. So this is really the integral from 0 to 2 pi of square root of 1 dt, and square root of 1 is just 1. So this is really the integral from 0 to 2 pi of just 1 dt, and the antiderivative of 1 dt is t. and I need to evaluate that from 2 pi to 0. So if I do upper bound minus lower bound, I get 2 pi minus 0, or 2 pi. So take a minute to think about what you just did, because it's kind of a big deal. You just figured out that the circumference of the unit circle is 2 pi using parametric equations. Good work. That's it for today.